I know it's going to be a bit hardest to present for hours just talking to myself and the screen, but I will do my best. The presentation I'm showing now is also available from this GitHub page. And on the same GitHub, there is a lot of code for different examples and etc. So unfortunately, it's all in Fortran 90. So if you're not familiar with that, I'm not sure how useful it will be, but there are good examples there of different assimilation methods, EnKF, ensemble smoothers, iterative smoothers, etc., that you can try out. This presentation is going to be quite basic. There will be a lot of mathematics or equations, but I try to keep it simple. And the idea is partly to introduce a lot of basic concepts in data assimilation. I know that people starting in data assimilation now are typically jumping on an established method and just running it. And it's easy to skip a lot of the fundamental derivations or interpretations that I think are quite important to have a complete understanding of what you are doing. So, and also this presentation is separated or split into a number of subsections. And I'm going to start with a simple problem. Okay, I'm going to use this one. And I call it the variational inverse problem. And this is more a motivational example that illustrates the problem with data assimilation. Why do we have to develop advanced methods for data assimilation? And it kind of, it will explain a lot of notation, basic notation in for the assimilation problem. So I will have a very simple equation. And what you see here is it's a scalar example. I have a model which is just dx dt equals 1. And it has an initial condition. So x of 0 is equal to 0. And then we all know that with the initial condition, this model has one unique solution. It starts in 0 and it has slope 1. Okay, so it's just a straight line. But in this example, we have another condition. And we say that the solution at time 1 is equal to 2. And that's impossible, right? It means that you cannot start with the initial condition, solve the equation, and end up in 2. So that means the problem is overdetermined and there are no solutions. And this is really what we are facing in data assimilation. We have a model with a unique solution, and then we have additional measurements of the solution. And that means the problem becomes overdetermined. So the only way we can solve for this is to allow for errors in either the model or the conditions or all of them. And that's what I'm doing here. I'm saying that my model is not perfect because there has to be some errors here if these conditions are both to be satisfied together with the model. So I say that my model has a model error, I call it Q, and it might be a function of t, time. And then both the initial condition and the final condition have errors as well. So now the problem now is that I have no conditions on these errors. So now the system is underdetermined and there are infinitively many solutions because I can choose A, B, and Q arbitrarily. Okay, so that means I have to make some assumptions on these error terms. And this is what I call my null hypothesis. And I say that Q, the mean of the errors, or the expectation of the errors, is equal to 0. So, yeah, so I have, it's kind of an unbiased problem. So the expected value of the errors is 0, but I have a variance. And here I just say that for the model errors, the delta correlated in time. So that means there are no time correlations of the errors. And both for the initial condition and the final condition, the error variance is equal to C node. And there are no cross correlations between these error terms. And if we assume these conditions on errors, what we are doing is to seek a solution that is close to the conditions and almost satisfies the model. And we do that by minimizing these error terms. So we want to find a solution that gives the solution corresponding to the minimum value of these error terms. So then we have to define some kind of cost function. Yes, and that's what we do here. We say that we define a cost function that minimizes the model error squared, and that's summed up or integrated over the time interval, the initial condition squared, and the final condition squared. So these error terms are going to be minimized. And this W0 is just the inverse of the error variance. Okay, so to minimize this functional, we can compute the derivative, or here I write the variational derivative, the definition of it. So an increment in the cost function given by an increment in the solution delta x, defined like this, should be order delta x squared when delta x goes to 0. And the reason I'm using a variational derivative here is that I have an integral up here. So normal derivatives becomes a bit more tricky. So we start with the definition instead. And if you evaluate these terms, then the cost function of x plus delta x, I think I'm just going to check something. Yeah, no, this changes all the time, huh? That's better. Okay. Yeah, so you just insert x plus delta x in the cost function, and we get this expression. And if we subtract j of x from this one, then you see that this dx dt minus 1 squared disappears, x node minus 0 squared disappear. And there are a number of terms that all include or are proportional to delta x, which is in here. And then there are some terms that are proportional to delta x squared, which I just ignore. And I say that if all this equation is equal to 0, that means all the terms proportional to delta x is equal to 0, then that didn't work. Okay, sorry. Yeah, then this expression will be proportional to delta x squared. So, okay, so and to set this to 0, we have to deal with this term here. And here we have the derivative of delta x with respect to t. And so we do an integration by part on this term. So, and that means we now have an equation where all the terms are proportional to delta x. And then we can see that for this to be 0, then since delta x is arbitrary, can be anything, then we need dx squared dt squared to the double derivative of x to be 0. So this term has to be 0. And then from this part and these two parts here, we get a condition on t equals 0 and t equals 1. And they look like this. And again, since this delta x is arbitrary, we get the model equal, or this model out here, the double derivative is equal to 0, and then we get a final condition from this term and an initial condition from this term. So we get a new system of equations, and these are the so-called Euler-Rogang, it's the Euler-Rogang equation. So it's a boundary value problem in time. it has a double derivative here, so it's an elliptic problem. And it has two boundary values at t equals 0 and t equals 1. And this has a unique solution. Okay, so, and to solve this, we integrate the model twice. So it's a straight line. This is the general solution. And if we apply these conditions, we get C1 equals to 4/3 and C2 equals 1/3. And just to show you what this looks like, we know the solution is a straight line. And if you solve the initial value problem, then you start in 0, and it's a line with slope 1. So this is the solution here. It's this dashed line or dotted line. If you solve the final value problem, then you start with a final condition here, and the solution is again the same slope line with slope 1. If you solve the inverse problem, this problem here, when we have this solution with these coefficients, we get this thick line. Okay, so what we see is that we get a line that's, or a solution that's relatively close to the initial condition, it's close to the final condition, and it's has almost satisfies the original model. The slope is a bit steeper, right? Okay, so this is basically the data assimilation solution of this problem, or the inverse solution of this problem. And what we are illustrating here is kind of what we try to do in all data assimilation examples. We want to find a solution that's almost satisfying the model and almost satisfying all the conditions, and also is close to all the measurements. There's another solution here. It's this one, and that's called the strong constraint solution. And that's where we assume that there are no model errors. The only errors are in the conditions, so in the initial conditions and the final condition. So then the optimal solution is actually the one centered in between these two lines here, okay? So that's a strong constraint solution. This full line we call a weak constraint solution because the model is a weak constraint to the problem. So what we have learned so far is that if we start with a model with conditions, then it has a unique solution. If we add additional measurements, this makes the problem overdetermined, and then we have no solution. So we need to allow for errors, and this again gives infinitively many solutions. So we have to specify some conditions on these errors. And then we can define these variational inverse problems and solve for a least square solution. And the least square solutions leads to what we call the Euler-Lagrange equation. And this is a boundary value problem in time. We saw that we could solve for a weak constraint solution that almost satisfies dynamics and data, or we can solve for a strong constraint solution that exactly satisfies the dynamics and is close to the data. Okay, so now is time for asking questions if there are anyone or any, but otherwise I just continue with the next topic.
You can raise your hands if you have questions, or you just, since no one's raising their hand, you can just jump up and ask the question now.
Yeah. Okay. I have a few slides on Bayes and its relation to the data assimilation problem. I'm not going to spend a lot of time on it because I will just go quickly through the slides to provide you the definitions. But I think the slides can be useful to look at on your own later on if you're not familiar with this. So Bayes' theorem is really the fundamental, well, it provides a fundamental framework for data assimilation. It's, if we start with Bayes, we can derive absolutely all the consistent data assimilation methods out there. And we can understand what approximations have be made. So it's a starting point for everything we do when we derive new methods. I think Laurent said once that if you cannot derive it from base, it's not the data assimilation method. But, yeah. Okay. Yeah, I skipped this. This is just some properties of a probability function, that it integrates to 1, etc. If we look at the definition of a joint probability, I'm using F for the probability density function throughout the presentation, I hope. And if this is the joint probability of X, as the probability of X times the probability of Y given X. And you can also turn this around and say that it's the probability of Y times the probability of X given Y. And if we solve for this F of X given Y here, we get Bayes' theorem. So what it says is that the probability of X given Y, which could be measurements, is given by or defined by a probability of the prior of X times the likelihood of the measurements, which is the F of Y given X here. And then there is a normalization that ensure that if we integrate this probability, it integrates to 1. So Bayes, this is what I said. And yeah, so this is just the way we are writing Bayes' theorem, where we have a state variable X, which can have a high dimension, if you like. So we have a prior probability of our state variable X, and we have a vector of measurements D, and which are described by their likelihood function. And then Bayes' theorem is basically written in this form. And I'm using D for measurements and X for the state variable throughout the presentation. We could say something about the likelihood function, because it's a bit a tricky function. It's not a probability density. So the likelihood function, it's the probability of the observed data for various values of the unknown parameters X. And it's something we use after the data are available to describe a plausibility of the parameter value X. And it doesn't have to integrate to 1. This probably didn't help at all, but the important thing, it's not a probability density function, and it's not a function of D, it's a function of X, right? But it's because D is given in this case. And yeah, I'm not going to go into that, but an example of using Bayes' theorem is given here. And this is a linear case. You have two Gaussian distribution. So I have a likelihood written like this, and I have a prior distribution like this. And Bayes' theorem just tells you to multiply these two together and normalize. And then I get a posterior probability, which is this black one. If you have something that's non-Gaussian, you still do the same thing. You multiply the likelihood with this non-Gaussian long tail distribution. And again, you get something, well, it's closer to Gaussian, but it's not entirely Gaussian, because you can see there is it's a bit steeper on this side than here. So in a way, the data assimilation problem is quite simple. If you know the probability function of the prior and the likelihood function, you can just multiply together and you have the solution. The problem is that in high dimensions, this is really not easy to do. It works well for a scalar problem, or maybe a one-dimensional, two-dimensional problem. Let's go back to this variational inverse problem again. So we had our model with errors like this, and we say that the error term, all the errors in this problem are described by Gaussian distributions. So that means if we multiply together these PDFs, we get an expression which is just e to the -1/2 of j of x, where j of x is this cost function. And that's exactly the same cost function as we minimized in the previous example, right? So Bayes' theorem leads to the least squares variational inverse problem for Gaussian error distributions. So there's a connection between Bayes and minimizing this cost function. Yeah, so Bayes' theorem defines the ultimate data simulation problem. It's impossible to solve in high dimensions. And Gaussian approximation is key and leads to least squares inverse problems. Of course, there are methods that don't make the Gaussian approximation, like particle filters, etc., particle flows. But I'm not going to discuss that at all in this presentation. Okay, so now I will continue with some linear estimation theory and discuss the update equations. So assume that we have a prediction or a first guess. We call it XF. So F can be mean forecast, or it can mean first guess. And then in addition, we have a measurement D. And we assume that this first guess is equal to the true value plus some errors. And the measurement is a measurement of the true value, and it also contains some errors. And again, we assume zero mean of the errors, and also that we know the variance of these errors, and there are no cross correlations. And then there is something which is called the best linear unbiased estimator of X. So you want an estimator that's unbiased, and it should be a linear estimator, and we want the best one. Okay, so suppose now we have the same definition again here, but I also have an update, which is equal to the truth plus an error. And a linear estimator, or a linear unbiased estimator, is we can write like this. So it's a number times XF plus another number times D. And for it to be unbiased, then if you have 1 minus alpha here, then you need to have alpha here, otherwise it's biased. So that's the one condition. And we want to determine alpha so that we minimize the errors. So by best, we mean minimizing the posterior error variance. So this one, the CA here. So if I start from XA, and which is X true plus PA, and then I insert this expression or this equation here, then I get an expression for the errors. So the analyzed error, or the updated error, is the error in the first guess plus alpha times the measurement errors minus the first guess errors. And this equation I can square and take the expectation to get an expression for CA, okay? So if I do that, I get this equation, which contains the prior errors for X, or the first guess error, and it includes the measurement error covariance here, error variance. So this is the posterior errors expressed in terms of the prior error and the measurement error and alpha. And I want to find the alpha that minimizes this error. So I can compute the derivative of C A with respect to alpha. So that means my best estimator is this one. And do I have a problem with my internet now? No.
Okay. You had a little cut or two, yeah.
Yeah. Okay, that's good. So I have this optimal blue estimator, and I also can evaluate the Kalman recognize this equation as the Kalman filter for a linear scalar problem.
The cuts are getting a bit worse somehow.
Yeah. So, but I'm not sure if it's me or.
I can still see the others move. Maybe we cut off our cameras and let you continue.
Yeah, okay. I will. I think my internet should be okay unless there is something wrong. But okay, there are some questions now. Let's see. It's a bit small for me. No, it's true. If you have, there's a question if you have additional conditions on this first example. Because I only have in condition and a final condition. If you have additional conditions, for example, somewhere in between 0 and 1, because I have defined my time interval, it just means you add additional equations. And extend the cost function. And it's still solvable in the same way. And then there's a question if why did we consider only the first two moments while forming the least squares cost function? Well, it's because we have shown that the priors are Gaussian in this case, so everything is Gauss linear. And then if you start with something Gaussian, you will also end up with something Gaussian. I will come back to issues with non-Gaussianity later on, but normally you would have priors that you define to be Gaussian or assume are Gaussian. And although this doesn't mean that posterior will be Gaussian if you have a nonlinear model, but for now we are looking at linear problems. Okay. So let's go back to the derivation I use now is basically the one used in the control theory and or estimation theory, and they are not used to including base in the discussion. Assume now that we start with base again, and we define a Gaussian prior for x and a likelihood function where defining Gaussian measurement errors in this case. And from base, we say that the posterior of x given d is proportional to the prior times the likelihood. And then we get this simple cost function. And now x is a scalar, and d is a scalar, so it's very simple. And again, we can compute the derivative of this cost function and set it to 0. And then you see here, you have an equation for x as a function of xf, the measurement, and error covariances. And with some simple manipulation, you get exactly the same solution. So the same estimator. So that means from base, we can also derive the same result with the assumption of Gaussian errors. So the blue is the optimal way of combining two linear estimates of a parameter. We can derive it from base formula when assuming Gaussian error statistics. You have base, you have the cost function, the least squares problem, and you get the updated for x and also its error covariance. So that was for a scalar equation. I will quickly show you what it looks like in if you have a vector state. And in this case, we have a state vector of dimension n and a data vector of dimension m. And these can be huge numbers. We have no restrictions on those. And we make exactly the same hypothesis. The only thing now is that we say that the measurements are related to the true state through a projection operator. And it's linear in this case. So that means that this H matrix is what we call a measurement operator that picks out values of the state vector at particular grid points, for example. So, and it can be any linear operator. So I have an example here where I have two measurements and the state vector of length 10. And so this is XF, this is my D, and H, if you define this as this matrix, it means that when I multiply H with my state vector, I pick out element X4 as the first measurement and element X7 as the second measurement. Of course, this can be made more elaborate. For example, this H could be a derivative operator that computes the derivative between 2 points. So it's 1 and minus 1 over delta X. Yeah, so, but the point is that we need some operator to relate the measurements, which are normally discrete and sparse in space, to the state vector. And then we start again from base, but now in vector form. And I'm basically omitting the normalization factor because it turns out that in the derivations I'm doing, I never need it. So I'm not solving for the full distribution. I'm just using this proportionality between the prior and the likelihood. And we assume that we are Gaussian prior and measurement errors again. There should be a transpose of these two, let's see, and same. No, it's correct. Sorry, my mistake. Yes, so we have the posterior PDF written like this, and maximizing this one is the same as minimizing this cost function again. And we compute the gradient. It looks like this. And with some manipulation, we can write the solution for X in this form. And this is what you see here is that this is an estimator where you solve the problem in the state space. You need to compute the inverses of this CXX, which has the dimension number of state variables. But you can rewrite this equation just splitting this into two terms. So I rewrite it like I have here, from here. And then you need to know about something called the Woodbury matrix identity. And there are two lemmas that you can derive from this, and they are listed here. And they say that this expression, which is basically what you have here, can be written in this form. And this other expression can be written in this form. And why would you do that? Well, if you look at this matrix, the update equation after using this lemma, you see that now you have a matrix inverse of a matrix which has dimension equal to the number of measurements. So you are basically solving the problem in observation space. And normally the number of measurements is much less than the state variables. So this is a more convenient way of solving the problem. It also means that if you look at this first part, this H transpose picks out columns of the covariance function. And the rest here is just a normalization. So what it means is that you add a number of columns of the covariance matrix to the prior to get the solution. Okay, so and the number of these columns is equal to the number of measurements. So there's one such column for each measurement. And there are two ways of rewriting this equation that are quite common. Let's see what I'm doing now. Okay, I will come back to that. And again, you can also compute an estimate of the posterior error covariance. And I put a star here, which means that I'm not going to spend time on this, but there is one derivation following on the next slides that you can run through yourself, which is quite straightforward. I'm giving all the details. And in the end, you get an update on this form and an updated covariance on this form. So this is the basic form of the Kalman filter update equations. And it's the one we are solving in quite a number of assimilation methods. Okay, in the control theory community, one defined something called the Kalman gain matrix. The Kalman gain matrix is just this part here. And we see we use it both in the update equation and the update equation for the covariance, posterior covariance. And then we can simplify the equations like this. And this is what you normally will see in the literature, or if you read about Kalman filters or Kalman filter applications. A problem with this equation is that in at least when we start working with ensemble methods, you will not compute this matrix, and I will come back to why. So it's an inconvenient form to have, at least for the computational algorithms. And then there is also something called a representative formulation that you should hear about. And it's, again, we have the same update equation here. And if I define these influence functions, again, like my R transpose, and this matrix is just my C inverse, and then I have the innovation, the difference between the measurements and the predictions here, I call that H. Then I can define a B that's equal to this C minus 1 times H, which is the solution of this linear system. Okay, and this is a system with the number of right-hand sides is equal to the number of measurements. Now, what am I saying now? Sorry, there's only one right-hand side here. Okay, I have these coefficients B, I compute them. The dimension of B is equal to the number of measurements. And when I solve for B, I can write the solution again as a linear combination of these influence functions. And I can also write C, the posterior covariance, in this form. And this is called a representative formulation. And in some aspects, it's an easier way to solve the, you don't have to formulate the full Kalman gain, and it's a more I would say, obvious way to formulate the equations. And yeah, I wrote also here that note that the covariance update is not, it doesn't depend on the values of the measurements, only on the measurement locations and their error variances. Yeah, okay, so a summary now is that we have introduced the concept of a measurement operator. We derived the Kalman filter update equations in the vector case, and we update both the state estimate and its error covariance. We defined a Kalman gain. We heard about the representative formulation, and we saw that we started with an original minimization problem, which had the dimension, the number of state variables. And in the Kalman filter update, we reduce the dimension to the number of measurements. Okay, let's see, there is a lot happening here. Are we also talking about representation errors here, or?
I have a word about that tomorrow, like the support
okay.
errors in geostatistics.
And well, the covariance matrices are per definition positive definite and have inverses. You don't really have to normalize, as long as you don't work with the probability density functions directly. And if you want to compute the posterior PDF, then you need to normalize the final update. I think that's what I can say about that. Okay, so let's continue. We are hurrying slowly towards the full data simulation methods. I'm going to talk briefly about sequential methods and smoother methods and how we obtain them from Bayes' theorem. And so we start from Bayes again. We have a prior of a model solution. So X is a model solution defined in space and time. So it means that we have defined a time interval, we have some initial conditions, we run our model forward in time. Okay, so and f of x is just the PDF of this solution as a function of space and time. Then we have a likelihood function describing the measurements, and the measurements are also collected over this time and space domain. Okay, so this is quite fundamental. It's I think this is the most fundamental equation you can write up for this problem, I think. And then we are going to make two assumptions. The first one is that the model is what I call a first-order Markov process. And that means it's a model that I integrate forward in time, and the solution at time I, it only depends on the solution at the previous time. Okay, so it's an explicit forward integration of the model in this case. And its first order means that it doesn't depend on any previous times. Okay, you can, given the solution at time I-1, you can compute the solution at the next time step. And it contains some errors, and they have a distribution. So this is this Q, I call this a transition density, is the model error going from time I-1 to I. Okay, and since the solution xi only depends on xi-1, we can write this PDF of the full model solution as, well, first we split x into a number of times. So it's for each time step, you have x node up to xk. And then we write it as a product. You start with the PDF for the initial condition, and you multiply with these transitions forward in time. So this describes the whole model integration over that time interval. And there are no approximations here if this assumption of the model being a first-order Markov process is correct. And of course, this is also valid for most numerical prediction models. We always have forward integration in time. Okay. So this is the first assumption. And then the second assumption we will make is that the measurements are independent in time. And by measurements being independent in time, we mean that there are no correlation between measurement errors at different times. And if the measurement errors are uncorrelated, we can also write the likelihood function as a product of likelihood functions for measurements at each individual time step. And this means that we allow for what we call a recursive processing of the measurements in time. And this is a quite strong assumption. I'll discuss it a bit more in a few seconds. But if we make these assumptions, then it means that Bayes' theorem can be written as this product of PDFs and likelihood functions. And the way it's written now, we have start with f of x0. We multiply with all these transition densities to get the model prediction. Okay, so we start with x0 here. We get the model prediction. and it's not influenced by any of the measurements yet. It's just a prior PDF for the model prediction. And then we introduce all the measurements, and we do it in one go. So we go from here to an update. If we write out this, these products, we can write it like this, and we can also rearrange the order of the terms. So we can, because this is just a multiplication of functions. So we can start with this one. We can multiply with the first of these for I equals 1, and then we can multiply with the first of these when j equals 1. Okay, so that means we are integrating from time 0 to time t1, and we introduce the measurements at time t1. So I start with 0, I integrate the model, I introduce the measurements. Okay, then I can continue the integration from x1 to x2 and introduce the next set of measurements. And this is, if we write this as a recursion, then we use basically the idea that today's posterior is tomorrow's prior, right? We start with the initial condition, we integrate the model forward in time, we condition on the first data set, which came here, so we get an update. And the update is of x node and x1, so it's also backwards in time. And I can define, if I want, I can define x node as being the initial condition, x1 to cover all the model solution over this time interval. Okay, so that means I compute a smoother solution, meaning that the measurements are influencing the solution backward in time. Okay, and then when I have this one, I put it in here, so it becomes the prior for the continued integration. I integrate the model forward in time. It's this one. I introduce the next set of measurements. So I update, and I also update backwards in time. And then we repeat this recursively until we have no more measurements. And this is what I would call recursive smoother updates. And it's different from what we had here. If the model, if everything is Gaussian and linear, then the solution from using these two different approaches will be identical. Okay. The advantage of taking this approach is that you keep the model on track. You don't allow the model to divert too far from the measurements, right? You introduce the new information as soon as you have it. And so you can, I'll show examples of why that's useful later on with nonlinear models. And then the last concept here is what I call recursive filter updates, because here we update backwards in time, but we don't really need that if we are only computing predictions. Then we need a good estimate at this final time, and then we predict. Okay, so what we can do then is to integrate away all the previous times. So we define, this is our estimate. We start with the initial condition, you integrate till x1, you multiply with the likelihood, so then you have an update of x node and x1. But now you can integrate away x node, and then you get a new prior for, you get an estimate of, how do I write this now? Yeah, you get a prediction at x1, and you have a measurement of x1. So this is Bayes' theorem for this, this solution here. And then you compute this update, and that becomes the prior for the next continued integration. And again, you integrate away all the previous times. So you get a solution for x2, given the measurement at x1 times the likelihood of measurement at d2. So that's the new update here. So then you have a filter solution. And the nice thing with this is that the solution at these measurement times will be identical to the solution of the smoother problem. So you are not making any approximations in the predictions. And this is really the basis for defining Kalman filter equations, or solving Kalman filter problem. So we need to know that the assumptions we have made is that the model is Markov process. We assume that the measurement errors are uncorrelated in time. Okay. And what I can say on this, I put it in red because this is generally not true. Still, in almost all data simulation methods, one will assume that the measurement errors are uncorrelated in time, because it basically makes the problem tractable and solvable. In fact, in most assimilation methods, people also assume that the measurement errors are uncorrelated in space, which is also not true, and it's an approximation. And the consequence of making this assumption is that the measurements get a too strong impact on the solution. So you get too close to the measurements and you underestimate your the true errors, or the true error variances. Okay, and the approximation is made basically to make the problem easier to solve numerically. But when we get to the ensemble Kalman filters, I will show that there are ways of getting around this. Okay, but so with these assumptions, we can process independent measurements sequentially in time, and the solution of one subproblem is the prior for the next one. So so there's a question, what is the fundamental difference between the filter and the smoother updates? There is no real difference. It's just that in the filter update, you only update at the final time where you have your measurement. In the smoother update, you also update previous times. And you will use, depending on the method, you do it differently. But I will show you examples very quickly, I think.